Oh dear. Right. Okay, 1.1. Systems architecture. Okay, purpose of the CPU. It doesn't do much. Its purpose is to execute instructions, control input-output devices. That is about it. It's not intelligent. It just does the fetch-execute cycle. Okay, fetches an instruction, works out what it is, executes it endlessly until you turn the power off. We look at the particular type of CPU architecture called von Neumann. This has got a few things that you need to know. It uses a single data bus to retrieve and store information between RAM and CPU. Instructions and data are in the same memory. I'll get a pen that works. Shared memory. So instructions and data are in the same format, binary. That means to the CPU, everything looks the same. So when it fetches information from memory, it assumes it's an instruction, but it could be data, which is good and bad. What it allows it to do is self-modifying code. That's where we write instructions that generate data, which are instructions. Okay? Which can be used for learning algorithms and lots of other things. Okay? Pretty handy. So that's von Neumann architecture. It involves a number of registers that you need to know about. Program counter. You need to know the purpose of the register though. The program counter holds the address of next instruction to execute. That's what it holds. It doesn't hold the instruction, just the address, the location of it. That value is passed to the memory address register, which is used to select a memory location. So it selects or specifies the memory location to access. It doesn't do anything else. It doesn't perform an action. None of the registers perform actions. When data is fetched, it arrives at the memory data register or memory buffer register. So that's the arrival point. If we want to write data from the CPU to memory, it goes via the memory data register. Okay? So the easy way of remembering what these are connected to is from their names. The data register is connected to the data bus. The memory address register is connected to the address bus. Okay, so the address bus is used to select where we want to access. The data bus is used as the transport for the data to and from the CPU. Okay? All of this is controlled by the control unit, which is not a register, it's a component. It performs the fetch, decode, execute. Okay? It tells all these registers what data they're needing them to do the job. When we execute instructions, these can be executed by the control unit, but if they are mathematical or logical or things to do with comparisons, that information is handed over to the arithmetic and logic unit, hence its name. Which again isn't a register, it's a component. So it performs addition, subtraction, multiplication. It does comparison, so is A less than B. And it will do and, not, or, and all those other logical operations, including shifts. Okay. Other than that, you don't really need to know much more, apart from the registers that are contained inside the arithmetic and logic unit, which are the accumulators. Just temporary registers for values that you're working on. Okay? So used during mathematical operations or whatever. The whole process of this involves the CPU connected to its memory. Okay, so this is the data bus. And that's the address bus. When we say memory, we mean RAM and ROM. The only memory that the CPU can actively interact with. If you've got files in your longer term storage, your secondary storage, they cannot be directly accessed. Anything that is in secondary storage must be copied to main memory first before you can use it. Okay? This interface is, in terms of how fast the CPU can work, relatively slow. So what we tend to do is we have a small amount of very fast memory called the CPU cache that sits in between the main memory and the CPU. This is smaller, but because it's closer, we can access it quicker. Okay? But we can't put everything in there, because that would be a great idea. It just has the most often accessed, it's a lot more complicated than that, but as far as we're concerned, it's the most often accessed locations. A copy. So instead of going to old slow memory, we can go to the cache quickly. So if you're processing an array, if you can put that array in the CPU cache, you'll be able to process it even quicker. Okay, arrays are actually quite quick to process, but if you can get it in the cache, it's even quicker. Okay. Right, and the fetch execute cycle, simple process. So we copy the PC to the memory address register so that we can select a memory location that we want to fetch the next instruction from. We then do a transfer. If we think of the main memory or main store as an array of memory locations, the memory address register acts like an index to it, and we can transfer that data to the memory data register. Then we can decode it, work out what instruction it is, then we can execute it. And then all we do is we do that whole thing again. And we just keep doing that until the power's turned off. If you've got a clock speed of 3 gigahertz, you'll be doing this 1 billion times a second. Well, you won't, the CPU will. Okay. What else we got? So, in general, if you've got more megahertz or gigahertz for your clock, the clock that governs the fetch execute cycle, your CPU will run theoretically faster. Okay, so if I've got a 1 gigahertz clock on the CPU and I've got a 2 gigahertz clock on the CPU, the second one will in general run faster. It depends on what you're actually doing. Okay, in reality what the instructions look like. But in general you would say, oh, that's going to run faster. The size of the CPU cache can vary. The bigger it is, the more expensive it is to produce and actually to purchase. but the more CPU cache you can have, the better. Okay, so if you've got 128k of CPU cache and you've got 256k of CPU cache, you're going to get more speed up because you're going to hold more values as copies. Okay, so by increasing that, you can get better speed ups. And the other thing we need to worry about in terms of speed is the number of cores. Okay, so a 1-core CPU executing a program compared to a 4-core CPU, you might think straight away, oh, it's got 4 CPUs, so it's going to be quicker. It depends on the application. If you've got a linear application that is just one thing after another, and you can't find any part of it where you can do 2 things at once, then having 4, 16, 100 CPUs isn't going to help you. But if you've got a task, like something like merge sort, okay, where you keep subdividing things and you merge things in pairs, if you've got 8 pairs of lists to merge together, you can actually merge sort, do them all at the same time. So if you had 8 CPUs, you could merge a list in the same time that it would take 1 CPU. So it has to be about the application you're running. If you've got an application where you can do 2 things at once, then you can take advantage of more CPUs. If you've got a linear application, then you're going to get no speed boost. And you have to be careful with this because often you will have higher clock speeds for single CPUs. You might have multiple cores, but they may be a lot slower because of the heat generated. Okay, and the electrical properties and things. So be very careful that you don't get caught out. If you get told that you've got an application that that is like one step after another and it can't be done in parallel, and they give you a fast single core machine and give you a slow multi-core machine, don't let them trick you into thinking that the multi-core is automatically faster. Okay, you've got to read the context of the question on that one. Right, carrying on. Embedded systems, which is a bit odd to put with the CPU architecture, but hey, there you go, that's where it is on the spec. Embedded system is a computer inside a device. Its purpose is to control that device. So it'll have functions that are important for that device. So if you've got a microwave, the embedded system is going to monitor the display. It's going to have several programs for the cooking. It's going to be able to handle the input devices that are on the microwave, which may be buttons, maybe dials. If you've got a fridge, probably a little bit simpler. There may be the odd button on a fridge to change the temperature, but it's maintaining that fridge temperature for you. So there is a simple program. So you would have a quite low power computer running that. But the key thing about the embedded systems is it is inside a device. It's not a computer connected, it's inside. Hence the term embedded. Okay, so that's component 1.1, systems architecture. Right, 1.2. Where's my bullet rubber gone? No. Right, 1.2 is RAM and ROM. It's basically memory. So we've got RAM and ROM. Okay, so we have, oops. RAM is volatile. It cannot remember unless you constantly refresh it. That requires power. Okay? So as soon as you remove that power, the contents are lost. ROM is non-volatile. So what that means is it does not require power in order to remember the contents. Okay? We have to power it to read it, but when we take the power away, it just remembers. So you get this in like cartridges. The main thing we use it for these days is like old consoles. Okay, you don't really use ROM chips much anymore, to be honest, but they're on old games, old console games. They all used to use cartridges because it's quick. Okay, you can access it as quick as RAM. Right, the other things that you need to realise about them: RAM, you can read it and you can write it. ROM, you can read it. In order to write to ROM, you have to follow a process, which is not often a repeatable process, depending on the type of ROM you've got. But in general, you write it once and then you use it. It's a storage. You might store programs, you might store data that's permanent, okay, in your ROMs. There's not much more to say about RAM and ROM, but they are both considered main memory. So they are accessible by the CPU. Okay? Right. RAM only holds two things. ROM the same. Instructions and data. They're the only two things that are stored. RAM is used to hold the current data we're processing, and the current programs that we're executing. Understand? If you have got any programs or any data that is stored on a hard drive or a solid state drive or on a cloud drive, then it has to be copied to the computer's RAM in order for it to be processed. Okay? There is another form of memory called virtual memory. Unfortunately, in a computer, we can only have a fixed amount of RAM. You cannot have an infinite amount of RAM. If we run out of memory, that means we can't load any more data, we can't execute any more programs. But there is another form of memory called virtual memory. I'm in the middle of recording a video.
So, someone's at the door.
I know they are, and I'm in the middle of recording a video.
So, open.
Right, so if we run out of main memory, what we can do is we can make use of secondary storage, so like a hard drive, in order to expand our main memory. Unfortunately, the CPU can't access this. So what we end up doing is swapping pages of memory that we're not currently using. We're not processing the data or executing the instructions. So we swap those to the hard drive, and the ones that we've got in the hard drive, in the virtual memory, that we want to process, we bring them back to our RAM so that we can execute. So what happens, the virtual memory on the hard drive, the swap disk as we call it, is acting like an overflow. So things that we don't currently need but we are in the middle of processing temporarily go onto the virtual memory on the hard drive. When we need them back in, we need to bring them back into memory so that we can carry on processing. So you end up with this swapping process. If you haven't got much main memory, RAM, you might find that you're doing a lot of swapping if you load too many programs up, or try and do too much work, or you've got a file that's too big to store in memory, which can happen when you're working on images for massive posters or movie editing. You might not be able to hold the entire movie in your computer's main memory, so it partly lives in the virtual memory. And when you're editing certain parts, it'll keep moving it in and out. If you end up doing the majority of your time swapping data to and from, because that takes time, you get into a process called disk thrashing. They should call it thrashing really, because you're like ruining your hard drive. It doesn't have such a massive effect with an SSD, because SSDs are a different type of memory, flash memory. Okay, they operate way quicker than a traditional hard drive. So you minimise this problem, and also flash memory has the same properties as RAM, in that you can access data from anywhere in the same time. Okay, with a hard drive, because you've got a physical mechanical device spinning, you have to wait for the data to be under the head that reads the data off the magnetic disk. So you've got waiting time. With flash memory, which we use in an SSD, you don't have that issue. Okay? So that's one reason that flash is quicker. It's not that it's because it's solid state, it's because there isn't this moving part problem. So it's quicker anyway. Okay, so if you really want to have very effective virtual memory, your best bet, if you're always editing large files and running lots of programs, is to use an SSD for your swap, your virtual memory disk. Okay? Right, that is basically the end of component 1.2. Okay? Okay, 1.3, storage, secondary storage. I think I'll go and get a new pen. Won't be a sec. I don't think I can walk that.
Achoo!
What kind of
Bingo!
Okay, we have got different forms of storage. Secondary storage. These are really crucial things that you keep making mistakes about. We've got primary storage. That's our RAM and ROM. CPU can access. Okay, which is why it's called main memory. That is short term. We're only using it to store the things we're currently working on. We have secondary storage. That is our hard drives. That is our SSDs. That is our USB sticks. Our flash memory. These are for long-term storage. Okay, the things we want to keep when we turn the computer, we power down. When we turn that computer off, we want to retain things. So we store all our programs and our data in files on these secondary storage devices. Anything we want to process has to be loaded into memory. So that's the purpose of secondary storage. There are different forms. We have got optical. So that's our Blu-rays, DVDs, CDs, which can come in read-only formats, but also you can get writable formats. But the writing is not quick, so it's no good for interactive things. So you wouldn't use a DVD rewritable to work on a project that you constantly need to keep saving. You're more likely to back up something to that or use it to deliver software. That software may be a film, okay, which is what we tend to use, although that's Dynadef anyway. We've got magnetic storage. That's what a traditional hard disk is, where you have a platter that is coated with magnetic material where we can store lots of noughts and ones. We can get a phenomenal amount of noughts and ones in a very small area on those. The packing density is amazing. But you also get tape. Digital audio tape, digital linear tape. We often use tape because it's super low cost and portable for backups. Okay, so when we're doing backing up of data, we might spool it out onto tape and then move the tapes and take them somewhere secure, which is what you're supposed to do. Okay, and then, so we've got the optical stuff, the magnetic, and then we've got this whole bunch of stuff that we now call solid state. So this is our flash. So you can get solid state drives, which are high performance replacements for hard drives, and you can get all different forms of what we tend to call pen drives or USB sticks. These small form factors that are highly portable. Solid state drives generally aren't portable, they're supposed to be fixed into a device. But the USB sticks, they allow us to copy data between. So when you get asked about these things, it isn't so much you know what all these different things are, it's the purpose. What are they most useful for? Follow the scenario. Okay? Secondary storage, as some of you say, is not for when memory fills up. Okay? That's not what it is. Secondary storage is for long-term storage. So that's how you should think. Long-term storage. I need access to it, but long-term. When the computer's off, I need to be able to save all that stuff. That's how you should be thinking when it comes to that. So they will ask you about and get you to think about these terms: capacity. How big is it? How much stuff do we want to save? Depends on the application again. The speed of it, access times. How quick can we read data from it? How quick can we write data to it? That depends on the applications again. Portability. Do we need to be able to move this data between different devices? If so, then you might use tape, but that's not very practical. But if you're going to move stuff around, you're going to want a USB stick. Generally, if you're going to move it physically around. Durability, a difficult thing to gauge. In general, flash devices have a limited number of writes from the way that they work, because they send high currents, or relatively high currents, to write data. You can only do that so many times before you destroy the device. Okay, so durability is a concern with flash devices. Now, SSDs have extra control and software that spreads the wear out across the device. So you're not writing to the same memory locations all the time. It spreads it about, so it evens that out. Normally, USB sticks don't have that sort of sophistication, so chances are that a USB stick will die quicker than a solid state drive. Okay? And that's the difference in the prices on these things as well, is that how good the control software is. So durability is a concern. Okay? None of these devices will keep things forever. Hard drive, 10 years lifespan. In general, I've got hard drives that have got stuff on from 30 years ago, but that's just look at the drawer. Chances are they could die. Okay? And you lose all your data. Reliability. that's going to be in conjunction with how it's being used. If you've got a hard drive and you're shaking it about, that isn't going to do it much good. That is not going to affect a USB or a solid state drive because there's no moving parts. So you're not going to damage anything. So you need to think about that. And then at the end of the day, cost. Hard drives are cheap. You know, you can get like a 4 terabyte hard drive for a quarter of the cost of a solid state drive. So you've got to like say, is it worth it? Again, it's scenarios. Okay, so that's the stories. That was 1.3. Right, networks. Remember, this is a huge section because it goes on for about 3 bits of the specification. So we got 1.4. Wired and wireless networks. Again, a lot of this is going to be, yeah, can you remember the stuff, but can you put it in context? Okay, so we've got local area networks and WANs, wide area networks. Do not just say that local stuff is local, near itself. You need to quantify. So if you're giving an example, you may say you have a local area network within a room or within several rooms on a site. It's important to quantify. Don't say they're near each other. What does that mean? It's a bit like all those words that you should never use without qualifying. Faster, bigger, smaller, greater. You know, all those things, they need explaining. So you can say those words, but you must explain them. Wide area networks are over a large distance, but you need to explain what you mean by large distance. So a good example of this would be if you had a school that was in multiple sites and you wanted to connect the school networks together, or you had a series of offices in different towns and you wanted to connect those towns together. That would be a wide area network. You've quantified it. Always quantify.
So,
Yeah.
for the wide WAN, you say that two or more computers and devices that are connected in different geographical.
Yeah, but quantify what you mean by geographical location. So say different towns, different buildings that are over a wide area or something. Yes, Peter. You could have a series of local area networks that are connected over a WAN, yes. Yeah, a bit, yeah, which is what, yeah, you tend to do. All right. Performance of networks. When you get quoted by your ISP that you've got a 200 megabit per second connection, they're quoting you the theoretical transfer speed, okay, between your device and their devices. If you're the only person using that, you might get that speed. But that's not how it works. Networks have traffic. Just like a road. The more cars that are on a road, the slower the road tends to be. Because you've got too much trying to go down one channel. So it is to do with demand. And you'll notice this when you're at home, that at certain times, weekends are usually really rubbish because everyone's connected on your network. At certain times, if you're in the middle of the night, you'll probably get good speeds because most people have sensibly gone to bed. Okay? But there are real horrible bottlenecks. Like the time when everyone gets home from school till about 9 o'clock is a terrible time. Okay? You might have, yeah, go on.
Is it better to address it through, say, traffic or what?
Traffic, really. Right, the other thing that can affect the network performance is noise. Okay? You tend not to have this problem with a wired network, an Ethernet network, but when you've got a wireless network, you've got lots of noise in the air, in the airwaves, and that can affect and generate errors. So when you get errors in your data transmission, which you can't get rid of these, even with a wired network, you get errors, okay? You have to retransmit data. So if you're retransmitting data, then that's obviously going to take longer. When you're using your mobile phones and you say, oh, my signal's really rubbish, you're actually still trying to receive data at the same speed, So you might have like a 54 megabit connection on your mobile phone, but because you're further away from the transmitter, you're going to get more errors, which means they're having to send the data multiple times, so the perceived speed goes down. So what you're talking about is the speed of the network, but also how quick you get the data. And if you get errors, you have to resend data, if that data is important. We tend to, with speech, it just cuts out, doesn't it? If you're talking on a mobile phone, we don't bother retransmitting the sound. You just go like, okay, let's see if we can catch up and get rid of the errors. But with data and programs, you have to retransmit. Okay, so you get a perceived slowdown. You're not actually transmitting data at a slower rate, it's just that there are so many errors that the speed looks like it's slowed down. What else have we got here? Right, client server and peer-to-peer. The server offers services to the client machines that are connected. Okay, so this might be a file server where you would store all your files centrally on one device, and then all the other computers connect to that file server in order to receive their files, which means you can move to different computers and still get hold of your files. The only downside to this sort of model is if the server fails, you've got no access to anything. Same with a proxy server for web access. Everything goes through that proxy server, so I make a web request from my client machine, and my network might be like this. Where I've got a number of workstations. And I'm making requests for web pages. So instead of connecting every workstation individually to the internet, which would be insane, what we do is we dedicate a server, which we call a proxy server, and we make requests to that server, and that server goes, okay, I know who you are, I will forward that to my internet service provider connection, go and retrieve the web pages, and then deliver them back to you. That central control allows you to administer the internet connection. So you can block certain sites. You can change the access of different users. Okay? You can log every single piece of internet access so that you've got a history. For when you get faults, it's like, oh, we can't connect to this server. Is it one workstation? Is it a workstation problem, or is it a global problem? Okay? Often when the internet goes down here, I might say to you, just see if you can get on the BBC or see if Google comes up. Just to see if it's a one-person problem, which sometimes it is. Maybe some settings have gone screwy. Or is it, whoops, the proxy server can't talk to the BBC's web server. Okay? So that centralized stuff allows you to manage things easier. But it does have that, if the central thing goes, boom, you're gone. The other way is to do a peer-to-peer. Where you don't have devices in overall charge. You share data between. So you might have, you can do this lots of different ways. You can still dedicate one of the machines to be in charge of something, but more in general, you just spread it around. Spread the data around so that you can access it from any location. Multiple copies. It's a little bit more complicated to set up and a lot more complicated to administer. So what you'll find in most networks, local area networks, wide area networks, you run a client-server model because it makes more sense. If you want like to just ad hoc connect devices together and then disconnect them again, peer-to-peer networks are really good for that. Okay, so you might do that if you're gaming and you just say if you're using a Nintendo DS, that uses a peer-to-peer ad hoc network. So there's like the PlayStation Portable and PlayStation Vita, if anyone's still got those devices. But you see that Samsung do it with their phones. Apple do it with their phones, where you can bring phones together and they talk. You don't like sign into a network or anything, you just automatically can talk to each other using that thing like near field communication. Yeah.
Can it be wired and wireless?
Yeah, you can do a peer-to-peer network wired, but it's more convenient to do it wirelessly.
So
Yeah.
what are the costs then?
Well, it depends how you govern the cost. If you're saying physically how much does it cost, if you're doing a wireless peer-to-peer network, you're not putting lots of infrastructure in. If you're doing a client-server network, you've got loads of cabling to maybe put in, you've got servers to set up and maintain. But the maintenance is easier. If you're doing a peer-to-peer network, that might be lots of other work involved in maintaining that. Okay? If it's a permanent thing, you're probably better off using the client-server model. Okay. Right, hardware, wireless access points, which is one of these horrible acronyms, which actually stands for loads of different things in computer science. It stands for wireless access protocol as well, which we used to use on mobile phones, WAP, before we all started going down the old 3G, 4G, 5G stuff. But yeah, wireless access point, this provides a connection to your network using a wireless, and then that wireless access point, which you normally do like that, might be wired back to your network. But you can roam and connect to that, and then the data gets transferred through your network. Routers and switches. Switches allow you to physically connect devices together using cables. Okay? The way that switches work, if you've got let's say we've got like a switch with 4 computers on it, and this computer wants to talk to this computer, internally the switch makes a connection, a physical connection for you. If you then want to talk to that computer, it makes a connection to that. So you're transmitting data between devices. A router is used to, as its name suggests, route packets of data to the correct destinations. Okay, that's the purpose of a router. Network interface card is how we connect our devices to the network. If we're wired, we can have wireless network interface cards if we're going to connect wirelessly. That's all it is. It's just a device that allows us to connect to the network. And then the transmission media, we have got wireless. Okay, so you've got different frequency bands for wireless communication, but you also have in each of those bands you have channels. Okay, and the channels are how those frequency bands are split up. If there is a lot of traffic on one channel, you're going to get loads of interference and errors, and you'll get slower perceived speeds. So what you try and do, and you can get software to do this, is to locate the best channel. In fact, the latest wireless routers will automatically do that and keep switching channels. Okay? That you communicate. So, but we've got different ranges for different speed settings, and they go different distances. You've always got a distance problem with wireless. The further you get away, the more errors you're going to get, the slower the speed becomes. Okay? If you're very close to the wireless access point, you'll get high speeds if there's not a lot of other traffic. The other method is to use a wired Ethernet connection, okay, which generally comes in a cable form, cat cable, okay, which is just a set of wires that are twisted around, sometimes called a twisted pair, that are used to transmit the data. Obviously, if you've got a wired, you've not got any interference. Well, you have got interference because you can have electrical noise and things, but you haven't got any interference from other people trying to use your wire. Okay? So you will always get higher speeds with a wired connection, in general. Okay? What else have we got? Domain name server is a computer that resolves domain names. So let's just see what a domain name looks like. So you might have something like this. bbc.co.uk. That's a domain name. On a computer somewhere, the domain name server, there is a list of all the .co.uk and what the IP address is of that computer that is serving the bbc.co.uk domain. When you type that in a browser, the browser goes to this service from this DNS server. It says, we're trying to find the IP address of this computer. What is it? It's looked up and we go to that IP address. What this allows you to do is to keep the same domain names, but you can change the server that is responsible quite easily just by changing the number. We wouldn't want to have to remember an IP address if we wanted to go to the BBC's web. I'm not saying that's the IP address of the BBC. But if we didn't have a domain name service, sometimes they screw up and the domains go down. Okay, .com went down for a few hours once, a few years ago. So no one could get to anything that ended in .com because the computer wasn't working, looking it up. But if you knew the IP addresses, you could just type them straight in. And the browser went, oh, you know where you're going, do you? This is how it used to be before the World Wide Web. Okay, you used to have to know the IP address of the computer you wanted to connect to. But you can still do that. The browser doesn't stop you doing that. If you ever need to connect to your home router to manage it or anything, you have to put the IP address in, don't you? Okay, so you can put live IP addresses if you know them, but they can be liable to change, which is why this is preferable. Humans like human readable stuff, don't they? Right, hosting. Hosting is just a service provider that allows you to put files. It depends what you're hosting. If you want to host some files, you might use a file hosting service, like Google Drive, OneDrive, whatever the equivalent Apple version is. I don't know what it's called. What's it called? iCloud. Yes. Okay, but you can store more than just files. You might have applications that you're running. You might have websites that you're building. And there are loads of different types of hostings. Ones that do all the work for you, some that just host the raw files. And virtual networks, which can sometimes sound confusing, but actually it's quite a simple process. In general, a network is a load of connected computers. So a local area network in a local area, wide area network in a wider area. But we can set up essentially networks, wide area networks, without physically connecting all the devices by using the internet. So we use protocols. VPN is the standard one that we all use, virtual private network, to enable a number of devices on the internet to act as if they're all in a local area network. They're not, because you're transmitting data securely over internet connections. Okay? But that in essence is what a virtual private network is. It is just using the internet as your network. Obviously, if you didn't secure it and you didn't encrypt things, that would be pretty dodgy and people could read all your packets and look at all your data. Okay? They aren't just for watching TV shows from America when you're in the wrong country. They are actually very useful virtual private networks. That tends to be what everyone associates virtual private networks with, is like getting access to something that's not available in your country. But they're more than that. Okay, so that's the end of 1.4. Right, network topology. Topology means layout. We have two that we need to worry about. The star network, where each computer has a single connection to a central computer, which generally will be a switch, which may then be connected to our file servers, our proxy server, our authentication server, which just is used to detect who's logged on, and then any other number of servers. Okay? Requires a single cable. If one of those cables breaks or there's a fault, you only lose that connection to that workstation. The rest of the network is fine. Requires a cable per workstation. Central resource management. Because all the devices are connected centrally, if you need to push updates to all the devices, you can easily do it. The mesh network. Or in a true mesh network, all devices are connected to each other. Okay? Don't put loads of devices on a diagram if you get asked to draw one, because it'll make it more complicated to draw. Do 4. Okay? In reality, if we add another item to the network, it has to be connected to all the other devices. So in a pure mesh network, you're going to get a big cost increase as you add more devices. Okay? So in reality, we don't do that because it's not very practical. So we do partial networks. And this is what the internet is. It's the best example of a mesh network. But it's not a pure mesh, it's a partial mesh, where we just connect to our neighbours. So you have a few different routes. Now what's useful about this and compared to the star network, if we lose a cable in the star network, that device can't communicate anymore. If we lose a cable in a mesh network, the device can communicate by going a different route. Okay, it's fault tolerant, but that costs. There is a cost because you've got to have multiple connections to other devices. How you physically do that, we're not going to worry about. You don't have like 10 network interface cards, you do it through switches. Okay, so you might have like a small little network connected to another network connected to another, so you can transmit. You're trying to avoid single point of failures, which is what star networks suffer from. Okay, you can still dedicate something as the server, but you give multiple routes to that. So this might be the file server. So I lose my connection, and you go, oh no, I've lost my connection to the file server. But I can still communicate with it by going round that way. A bit longer, but I can still communicate to it. That's how the internet is set up. Right, talked about it's important on networks to encrypt the data. If you're using Wi-Fi, Wi-Fi is what we call a broadcast. When we're broadcasting, that means it is not going to just one device, it's going to all the devices that are listening to those broadcasts. So if you do not encrypt your data, everybody, every device will be able to read that data. So it's important that when you're using Wi-Fi, you encrypt. With a wired network, you're technically not in the same situation. You would have to physically attack the cable in order to get access, which is not very hard to do, to be honest, in order to get access to the data. So really you should encrypt down a wired network as well. If you don't, you're leaving it open. Right, MAC addresses. They are device identifiers. It is not the same as an IP address. Okay? An IP address is a network. So this is a device address. This is a network address. You can use MAC addresses to block devices or allow devices. Okay? IP devices are assigned by the network. MAC addresses are defined by initially a hardware manufacturer, but they can be changed, MAC addresses. But they're done by an administrator. Okay? So you can, on a network, you can allow access to certain MAC addresses and block all the others. So it's quite easy to block access to your network using the MAC addresses, saying only these network devices can connect, even if they're pretending to have your IP address. What else have we got? Right, and then we've got the protocols. So we've got TCP/IP, transmission control protocol, internet protocol, used to transmit and identify devices on the internet. Okay? It is an open format, which is why it's been adopted for the internet. We have got HTTP and HTTPS. These are for requesting data from web servers and communicating with web servers. Hypertext transfer protocol. The S means secure. So the difference between those two is data that is leaving the browser is encrypted before it goes, and data leaving a server is encrypted. So the communications are not hackable. You can intercept the communications, but you won't be able to read them because they're encrypted. If it's using HTTP, it's plain text. You can read the data. FTP. Tend to not use this directly anymore, but this is how we used to connect to servers that contain files. So you get the IP address, you live connect to it, and you see folder structures. Just like if you were browsing your own computer. You had to know something about the computer's structure, the way it stored everything in order to access. This is why we've got the web now. Okay, because this was too much for most people. It's not a general use thing. Okay, but that's file transfer, for transferring files between devices. So you've got a server device and a client. You connect to the server and say, all right, I want those files, or I'm going to upload those files. Okay, and you transmit them, and they're downloaded. And then we've got all the messaging things. We've got post office protocol, which is about organising mailboxes, having like contact lists and things like that. We have got SMTP, okay, and we've got IMAP, which are the ones to allow us to access mailboxes. They're basically, they do the same function, they allow us to read things, but they work slightly different. IMAP gets a copy, doesn't delete anything from a mail server. SMTP actually does a transfer. So if you read an email, it's taken off the server. Okay, that's really the main, there are other differences, but that's the main one. So IMAP is the one that we tend to use, because it allows you to look at your mail on different devices without destroying the original mail content. Okay? Right, and then layering. The reason we use layers. And I'm not going to give you the full layer model, I'm not bothered about that. But just to illustrate the concept, at the bottom, what is the bottom one? The data link or link, yeah. What's the one at the top? Right. Okay, so if I'm web browsing, I'm going to be using the protocols for the application layer of TCP/IP. Okay. The data link layer is how I'm connected to my network. The reason we layer protocols is so that we can change a layer without affecting other layers. So the web browser does not need to know whether I am wired or wireless, or using mobile data or Wi-Fi. They all have different settings in the data link, but when you're using your browser on your phone, if you turn your mobile data off, you just switch over to the Wi-Fi protocol, but that doesn't affect the browser. The browser might get a lag because it's lost network, but it'll then come back up. But it doesn't affect how the browser works. It's just saying, well, I don't care how you connect it as long as I keep getting my data. Okay? As long as I make my request, what are the other two? No, I've got data links above.
Network.
Which one's at there? Network. Right, so it allows you to switch the sub-protocols that you're using without affecting the other ones. So it's quite important. If it was all one big thing, you'd have to like say, well, let's stop doing that. We'll have to like restart a session or something. So it enables you to switch things out. That's why we have the layers. There is actually, the full model for this is like 7 layers, but we don't need to learn that. You used to have to learn it for A-level, but it's not even in the A-level now. We've dropped down to this, weirdly. So we're doing A-level computer science, basically. But yeah, that's why we do the layers. So it allows you to switch without having an effect. Okay? It's going to have an effect on the adjacent layers, okay? But it shouldn't affect this layer. The browser shouldn't be affected. As it's saying, well, I'm just making requests down all these layers. I'm making requests, and then this is the physical thing that happens in the end. But how that happens, I don't care about. I'm worried about all this. I have to make requests at the transport layer. That's what the browser's got to worry about. So if I'm not using TCP/IP, which is what these two are about, okay, I can switch it out and use something else like UDP or UPT. I can switch it out and use a different network protocol, which is slightly different to TCP/IP. That would start affecting the application thing because it's there. But if I change these are the two that we switch around the most, how you physically connect. So that's why your computer, your laptop, if you plug in a network thing, it goes, oh, there's a network, I'll use that, it's faster. So it switches that protocol at the bottom, but it doesn't affect you with what you're doing. It just carries on seamlessly. Right, and the last bit on this bit is packet switching. Remember, that's what TCP, the transfer control protocol's in charge of. So, data broken into packets. Each packet is numbered. In general, each packet the calculator checks them for. Remember, the checksum is there to try and verify that it arrived correctly. Okay, there are a lot of other things that are done, but we have sender address, and that's the IP, destination address. Is attached to each individual packet. You might also have other things about how big the packet is, size of the packet. Again, so you can verify it's been received correctly at the end. Yeah, type of data, whether it's streaming data, so it might be stream, or whether it's just like fixed data. That's important because when the packets don't arrive at the other end, if it's fixed data format, we need to request they come. Because if you've got half of a Word document, that's no good to you. If it's a stream, you go, well, actually, by the time I get that data back, it's too late. I'll just ignore it. And that's how you get that breakup. So we like go, just keep chucking the data at me, I'll see if I can get something sensible and move forward. So sometimes you do get breakup. If you've got like a, I know in one of my rooms, the connection from Virgin is really rubbish into the box, so it like breaks up from time to time. I need to put an attenuator on it or something. Anyway, something else. Right, so we do this, the data, we break it into packets, and then we transmit it across our network. So our network is a partial mesh, or a mess, could be a mess. And we may be transmitting from here to here. Each packet makes its own route to the destination. And this is the crucial thing about packet switching. So if I've got 3 packets, packet 1 might go this way, and it's taken 4 moves. I'm going to cheat. Packet 2 might go that way. So 2 moves for packet 2. And then packet 3 might go this way. That would be unfortunate. 6 moves. The crucial thing about packet switching is the packets do not arrive in order, because we do not know how they got to the destination. They make their own way. They are routed through the network, depending on lots of factors. One of them may be traffic on a particular connection. Okay? So what we have to do at the other end, when we receive these packets, check some, make sure it's been received correctly. If it hasn't, potentially request. If we've got a broken packet, re-request it. That's why we need the sender address, so we can go, we can say, oh, oi. If you didn't, you say, where did I get this from? Like you do on some eBay things, and you go, where did this come from? I don't know, I did. Because you bought it when you can't remember what you bought. I do that all the time. Right, so we check the checksum. We then reorder the packets. So we may use a buffer for that. If you've ever used a torrent program, you'll see it put in the packets. They usually have a little graph at the bottom that show you all the packets that you're expected, and then they colour them in as they arrive. So they don't all arrive zip like that. It's all over the shop. And you can watch it. They're quite fascinating to watch. And you go, oh, come on, which one's going to come on next? Oh, no, I'm waiting for that packet there. So where is it? It's coming from, and that's a good example of how this sort of network works. Because the stuff can be coming from lots of different places. It still doesn't matter. It's just coming different routes. So once we've reordered it, and we've verified that we've got all packets, then we can actually use the file. So display document, whatever it is. Okay? Packet switching is pretty cool. It's what makes the internet work. Took ages to get it to work properly as well. Right, I'm getting there. 1.6 is the next one. I think there's only 1.8. Right, security. We've got different things to worry about for security. So we've got threats and mitigation. How do we get around those threats? So the threats are multitude. You've got direct access problems, okay? So you've got internet threats, which may be people just trying to connect to your network. The easiest way to protect a network from the internet, don't connect it to the internet. Then you cannot have anyone hack you from the internet. But, one of the things you do when you're designing networks, you say to yourself, does this network need access to the internet? If it doesn't, why give it access to the internet? If it's for convenience of administering the network, does that outweigh the potential threats? Everything is all about policies. Okay? The way we stop these things, because a lot of these attacks have to do with people. manipulating people, so phishing attacks, trying to get people to cough up information. Okay, you're phishing for information. It's not about, the phishing attacks come in lots of different ways. They can pretend to be certain bodies like banks, utility companies, whatever that may be. Maybe you sometimes get these random things from like DHL, you now need to pay your invoice, or we tried to deliver your parcel, click this PDF and we will show you the receipts, and it's not a PDF that's showing you a receipt, it's a virus that they're trying to get you to activate because you have to manually activate. Okay, so it's not just about what comes through. So email's one way of doing it, but people can fish for people's usernames. You can do social engineering to find out what someone likes to have. If you know the format of a username and you want to work out a password, people use silly common passwords, don't they? People use children's birthdays and names as passwords. So you might be able to guess. You could force someone to tell you their username and password. You know, if you were very desperately wanting to get on this network. So you've just got to bear in mind all the different methods. So viruses, Trojan horses, okay, malware. We can put software in place, but software is not infallible. You can have virus scanners, malware checkers like Malwarebytes, that sort of stuff. You can make sure you're doing backups, but you want to, the weak link is us. Okay, and we have this really naff system, usernames and passwords. Usernames, you can work them out. You know, there's normally a format to usernames, just like ours are. So once you've found out one username, you might be able to work out all the others, and then it's just a matter of getting the passwords. So you have to have password policies. Don't write passwords down. Don't have passwords that are a single word. Make sure people use funny characters to make the passwords stronger. They're not impossible to crack, but you make them more difficult so that it's not easy to use things like dictionary attacks, where you just run through a dictionary trying every single word. Okay? If you at least combine two words together with a funny symbol, you're making that harder for somebody. But you can put policies in place that say, if the password's wrong 3 times, block the account. It's standard practice on administration accounts. Okay? Not everybody does it. You don't have to have a password, which would be insane on an internet-facing network to not have passwords. Okay? So, in the thing, the specification document, it just reels off all these, so just make sure you know what malware is, phishing is, brute force attacks, denial of service attacks, where you just bombard a server with requests. Servers can only handle so many multiple users at once. So if you can send enough requests, you can take a website out. Websites are quite good at protecting against denial of service. If you were to try and do it with a single IP address, they would be able to block it. That sometimes happens with proxy servers at schools. If everybody signed up on the same day to a Google account, Google might go, whoa, hang on a minute, we're getting multiple account registrations from the same IP address, because it's all through the proxy server with one IP address. At my last place, we used to get problems all the time with this, and we used to get like Google blocking us. And we used to phone them up and say, no, it's not a botnet. We're not trying to take Google out, it is just a college. Okay? But that's why they try and infect lots of computers so they can take over computers to do denial of service attacks. For hire, usually, as well. Right. Intercepting data, if you encrypt, it doesn't matter if people get your data, they can't read it. So keeping things in plain text in files is really dodgy on a network. You should not have a list of usernames, passwords, user details in plain text. It should be encrypted. And then if it gets stolen, it doesn't matter. SQL injection, remember that is the way of adding in input data SQL commands to do things with the database. Okay, you can block that by default. So a policy that the network administrator uses should be to not allow any non-alphabetic stuff. So don't let them put SQL statements in input boxes for their username. Don't let them put tags like this. So like script, source, equals, and then go off to some web server somewhere that's got a malicious script on it. Don't let people put the tags. End up. Then they can't do it. So there's all these attacks. Just read the thing on that. There's no point in going on it too much. Right, finally, system software. Purpose of an operating system, it's a manager. The OS. It is a manager. It manages the computer. It manages the resources. The resource of the computer. The resources are finite. So you've got your storage. You haven't got an infinite amount of storage. You haven't got an infinite amount of memory. And I mean secondary storage when I say that. It's like your hard drive, your SSDs. Your main memory is finite, so you have to manage it. Your CPU, every program you've got running wants access to the CPU. So that has to be managed by a scheduler. Decides who gets to execute on the CPU next. Okay? Users, accounts. When you log in, the operating system is managing. It gives you access to your resources when it's authenticated you. So who are you? Right? So you put a username in, say, it's me. Then it says, what's your password to check it is you. That's authentication. So all these things are resources that the operating system manages. Okay? Virtual memory comes under this. So that's managing the memory in the CPU that the programs are stored in and the secondary storage. That's a task that is done. File management, which sounds lame, but just organising things into folders, allowing you to move things around. The operating system is having to manage all that for you, so that you don't rename something that you've got open. It moans at you and says, oh, you can't, you've got it open, you can't rename that file. Can't delete the file that's in use, all that sort of stuff. But they are the tasks that the operating system does. So it is not a utility. The operating system is system software. Utilities are the programs that help manage the computer or maintain it. Loads of different types. The exam board are obsessed with defragmentation. But you can have copying software. You've got obviously your virus scanners. Try not to duplicate yourself. Don't say virus scanner, malware scanner. They're the same thing, aren't they? They're blocking access to stuff. But things like firewalls, which is slightly different. Firewalls block physical access. Okay, that's what maintains a list of like MAC addresses that are allowed to connect to your network and things like that. So you can set that up on your home network. If you know what devices you've got, if you put all your devices on and connect, and you can go onto your router, onto its firewall settings, and find out what devices are connected. Say only allow these, don't allow anything else. And then anyone set outside your house can't use your network. Okay? Utilities are there. They're the programs we don't want to use, but they help us maintain the computer. The stuff we want to use are our applications. That's the programs we want to run, the jobs we want to do. Word processing, spreadsheets, databases, presentation software, graphics manipulation software. Okay? Web browsers. They're the applications we want to use. Media players. Utilities, I'd rather not have to know about it. In an ideal world, you shouldn't need to know about an operating system to use a computer or any utility software. You should just use the computer. And if you think about it, things like Alexa and Google Home and whatever the rubbish that Apple made is, they are taking that concept forward, aren't they? You just talk to it. They're useless and rubbish, and they're basically just a Google search. They're a little bit more than that. But that's the way it's going. So in an ideal world, you won't be worried about, have I got Mac OS? Is there a Linux version of this? Is there a Windows version of it? You should just be, I just want to run it. But unfortunately, we do need to be aware of this in order to use a computer at the moment. It's better than it ever was. At least we've got graphics interfaces to all these, which we never used to have. You know, when the old flashing cursor, when this used to be what greeted you when you turned your computer on. We've moved a long way. You still use that mode because it's quick. If you know all the commands in your head. Which, if you're using the computer all the time, it's not hard to do. Okay? Oh, that was another one. Backup software. Yeah. A full backup, it takes everything and dumps it. Incremental is what you tend to do after that. So that you just save the changes, the things that have changed. Otherwise, it's too big a job and too much data. Okay. Right. Encryption software, often built into the operating systems these days. Some of these you can turn on and off. BitLocker is the Windows one, I think. Okay. But similar systems exist in other operating systems. Right. The only other thing is the legal ethical stuff. You can't really revise it, but you've just got to make sure that in questions about that, you consider both sides. It's always going to be a discussion. So, pros and cons. So think about who are the actors in the question. Okay? Stakeholders. Always try and gear your answers back to the stakeholders. So, right, the technology. What technology is there? How does that affect the stakeholders? What are they going to use that technology for? How does that affect? Good and bad. You know, in order to use that technology, does something need to happen? What if that thing doesn't happen? Okay? It's all about showing both sides and then coming to a conclusion. It does not matter, there is no one answer to these things, but they want to see a balanced view. That's the trick on that. So make sure you haven't gone like, oh, I think this is brilliant, and then that's all you've said. You've got to say, yeah, I think this is brilliant, but actually there's some other stuff that's not so brilliant. Okay, pros and cons. Fill me out now. Right, okay, so I will put an index on all that junk. That's the first paper. I think I've got a lesson on Tuesday. I will do the other one on Tuesday, paper 2. Which is going to be a bit trickier because that's a lot of pseudocode stuff. But I will do it. Okay, cheers guys.